Hi, Paul. It's a pleasure to have you here for our webinar session.
Hey, Lucas, thank you so much for having me with you today. It's a pleasure to be with you.
Great. We will see here different interesting things about HPC in the Microsoft Azure Cloud, together also with some interesting ISVs. One side we have PTC here, on the other side we have ANSYS here, and we will show a whole workload for engineers, how they can move the process to the cloud.
Sounds awesome, Lucas. Looking forward to exploring further with you.
Great. So let's have a jump to our agenda. Okay, like I mentioned before, so we do the introduction together now with Paul. We will start immediately. Then we will see this amazing process, how easy it is for different parts of a company in the R&D section to engineer a product and then do the simulation. And this all virtualized on Microsoft Azure Cloud. Then we will see a little bit more deep, a little bit more into the calculation about pricing with consumption-based resources, one on the Azure cloud things, and the other side on how it could look like, for example, with ANSYS dynamic licensing. In the third step, we learn a bit more about PTC Creo, how PTC Creo is performing in the cloud, and then we will do a short outro. Paul, why you don't tell us about something what you and your team are doing?
Thank you, Lucas. Well, again, my name is Paul Rousell. I lead our EMEA Azure HPC business and team. We have a number of HPC dedicated specialists and technical specialists that are really committed to helping our customers run their HPC workloads on the Azure platform, and really committed to their success, unlocking their innovation using our platform. So we've got skills that span technical depth, sales leadership, industry expertise, business development. And as part of that, when we think about how we really unlock customer success and power our customers' innovation, we can't do that on our own. We absolutely partner strongly with a number of HPC specialized partners in the marketplace. And it's a pleasure to be with you today, Lucas, with Desktop Studio.
Thank you very much, Paul. Okay, we as Desktop Studio, together with Microsoft Azure Cloud, we enable engineers and construction teams in companies to enable innovation through cloud.
That's great to hear, Lucas. We'd love to learn more about the projects that you've been working with your customers on, how you've been partnering with your customers and with Microsoft to really unlock their innovation and fuel and power their success. Please, could you share more?
Yes, please. We have here several success stories where we enable such customers in different industries to drive innovation in the public cloud. Here we have a really nice story together with a nuclear power plant in Switzerland, where they have run their part of their security approval for their nuclear power plant to get it back online.
Wow, thanks for sharing, Lucas. So here you've got a case of, with a combination of Desktop Studio and the Microsoft Azure platform, how we're supporting critical infrastructure through using the cloud.
That's true, yeah. Together with Microsoft Azure Cloud and through the whole compliance and governance, they will be able to run such critical workloads in the cloud. But we have also other nice success story in case of innovation. For example, here we have a project here. Some guys from the French-speaking part of Switzerland, they will engineer a sailing boat who should reach 100 knots. So this means about over 200 kilometers per hour. So this is also really amazing. And if you imagine all these guys here, like Bieno and his team, about 35 employees, these guys has no clue about technologies. They have no clue about how to set up Linux clusters, etc. But these guys are are able together with Microsoft Azure and Desktop Studio to run specific workloads like CADFEM or ANSYS in the Microsoft Azure Cloud.
So what I'm hearing there, Lukas, is the capability that Desktop Studio provides really helps to make HPC capabilities, the power of HPC in the cloud, accessible to more people, where they don't need to have deep HPC backgrounds and expertise in order to harness the benefits of this HPC capability.
That's exactly this. For example, here we have an enterprise customer. They do their whole research and development in a Microsoft Azure Cloud through us. And these engineers, again, they have no capabilities about Linux and clusters, but they know exactly how they need to do their simulation to get the best results. And this is exactly where we as Desktop Studio step in to enable engineers without deep IT knowledge to run such heavy workloads in the Microsoft Azure Cloud.
Fantastic. So abstracting IT from HPC so that engineers, researchers, scientists can harness the power of HPC without needing to understand the infrastructure that's powering that HPC workload. Super to hear. Thanks for sharing, Lukas.
Thank you, Paul. So let's start with our webinar session.
Awesome. Thank you for today's session. I'm really looking forward to learning more and partnering with you.
Thank you, Paul.
Hi, my name is Thomas Diehl and I work for PTC as an application engineer. Today I will talk to you about Creo and why the latest Creo innovation makes sense to combine it with Microsoft Azure, Desktop Studio and ANSYS solutions. Now let's see and come to the fun part of my presentation, how the Creo Simulation Live Plus comes to the engineering desktop. We just connect through the Desktop Studio app to the website, authenticate, download the client, connect to the right CAD machine. Easy, straightforward, and scalable. Now connected to the perfect CAD software, we see Creo live in action. Creo now showing our engineering dataset. It's a pipe construction with a kind of valve. Firing up now the live simulation, and we're checking the as-is situation. Firing up the live simulation enables us to have the instantaneous feedback from our design. We have an inlet. Above the valve with a temperature and a flow. The valve can be opened and closed. So this is my mechanical situation. Now starting the simulation. So during all design changes regarding geometry or the angle of the valve to be open, my simulation is associative. Opening this. As you see, it's a bit fuzzy. Now opening, the valve gets opened, and now the simulation starts to rerun. And as you see, there's mass flow through the side arm where the hot water gets soaken in the mainstream and starts to mix. Okay, this is my as-is situation, but my design task is to see how the situation and my design behaves in a longer pipeline. But before that, we can just review the different capabilities we have in that app. We can not only display the velocity, we can also switch to the temperature and see how the different temperatures and the mixture behave, switch back to velocity and see how the result at that point in time is behaving. So final task, we just stop the simulation and I'll add another piece of pipe. Therefore stopping it, and switching over to the modeling task and assembling here another pipe. Quite easy, straightforward. Just hit the assemble button here, search for the additional pipe, place it in my assembly, attaching that. So this looks good. And now changing the fluid situation, so lengthening the fluid. Activating it and attaching it to the end of the pipe by flexible modeling move. Just here, hit the move command, pulling the geometry, adjusting it to the end of the pipe, and now my design change has been done. You see the probes have been associative, so the temperature, max temperature probe, and also my velocity probe. And now we are ready to activate the entire assembly with its simulation and turn on the simulation display. Now here we see how the velocity and the hot water here on the temperature plot gets displayed, how it changes. So we have an initial first step, and then over the time our temperature rises as more and more hot water comes to the end of the pipe. This shows how easy it is to use the Creo Simulation Live and Plus extension, and how easy it is to deliver that powerful engineering solution to the engineer's desktop via Creo, the Creo ANSYS powered products, and Microsoft Azure combined with the competence of Desktop Studio. For a final validation, we will then pass on this model to the calculation department. They're doing their simulations on ANSYS, and now you can see how ANSYS is behaving in such an environment.
Hi everyone, my name is Demian Lauper and I am a simulation engineer at CADFEM Switzerland. Okay, let's continue with the CFD simulation within ANSYS Fluent. First, I want to resize my cluster to 10 nodes, so I will have enough HPC performance for my simulation afterwards. This will take a few minutes to resize. In the meantime, I can create my mesh that I will use for my simulation. By clicking on the connect button here, I can generate the exe file that I need for setting up the remote desktop session. Here, let's start Fluent. And I'm going to use 40 cores for meshing, so this is already set up correctly. Since I have a clean geometry, I can use the Watertight geometry workflow, which is quite fast and easy. Load the geometry, maybe do a quick inspection. So we can see here that this is the geometry with the valve position as my colleague left it for me, because he has already tried this in Creo Simulation Live. We saw this just before. Since there is quite a narrow gap here, I want to refine this with a local sizing. I use a proximity sizing with maximum of 10 millimeters and 8 cells per gap. For the global mesh settings, let's use also 10 millimeters, curvature angle of 12 degrees, and 3 cells per gap with respect to edges. So we now can already see the surface mesh. Next, there is a task with a few questions, such as the type of my geometry. I select here both fluid and solid regions. The rest can be left as default. Same for the next few tasks. They are already correctly pre-filled. I can just click through them. In order to adequately resolve my boundary layer of my fluid flow, I'm going to use an inflation layer here. I'm using 8 layers and an improved transition to the bulk mesh. Last, I'm generating the volume mesh. I'm using polyhexcore, also known as mosaic meshing, with a maximum cell size of 8 millimeters. This will then be corrected to a useful value for the mosaic mesh. So let's generate the volume mesh. Okay, so now we have our volume mesh. The mesher created 2.4 million cells with a little bit under 2.5 minutes. We can see here that we have a very nice hex core mesh in the bulk of the volume, as well as a polyhedral mesh in the vicinity of the walls. Let's save the mesh file. Okay, so let's now go check if the cluster is ready. We can now click here again on the connect button in order to create this Excel file here. But this time we copy this to the desktop of our virtual machine. And we execute this directly on our virtual machine. This will now set up the cluster in the background and make all the configurations that are necessary. This starts now the Fluent launcher, which is already pre-configured, as we can see here. Also the 440 cores, they are already entered here. This starts now the graphical user interface of Fluent on our cluster. So let's load our mesh file. We can copy this from the desktop, can copy this directly into our working directory on the cluster. So we have access here now and can load this into Fluent. So the mesh is loaded into Fluent. We can visualize this here in our graphics window. We can see that this is the mesh that we created before. I will do now a very basic setup of the same simulation that was done by my colleague before in Creo Simulation Live. So of course we need the energy equation to be solved. We need water instead of air. So let's copy water into our project. And also for the solid material, can also copy steel into our project. So now we got all the materials we need. Let's assign them to the correct volumes. Our fluid volume will be using water. And our solid domain will be set to steel. So for the boundary conditions, inlet 1 is the top inlet. We set this to 20 meters per second and 80 degrees Celsius. And the second inlet, we have 20 meters per second and 20 degrees Celsius. Our outlet condition, let's have a look here. 0 Pascal back pressure on our outlet towards the atmosphere. This is okay like this. The rest we can leave as default here. Let's set the number of time steps. So we use a timescale factor of 2 for our fluid domain, timescale factor of 1000 for the solid domain. We will just do 100 iterations here just to see how it runs. Of course, this simulation would need a lot more than 100 iterations. Okay, so let's start the simulation. Let's keep in mind that this is a 2.5 million cell mesh here that we are now using for our simulation. And the solver runs quite swiftly through these many cells. Okay, so this was our 100 iterations. Let's quickly create a plane for using for the contour plot. Let's create the XY plane. And let's display the velocity on this plane. You can see here the velocity magnitude around our valve. Or we can also visualize the temperature. So this is how you use Fluent on a cluster on Desktop Studio. I hope I could show you a lot of interesting stuff, and thanks for watching. In my part of the presentation, I want to talk to you about the benefits of cloud hardware from a CFD engineer's perspective. First, I'll introduce to the topic with an example that every simulation engineer knows. After that, I'll get a little bit into scalability and how to save cost with a on-demand licensing model. And in the end, we have a look at a few benchmarks. So this here is the hardware demand of an exemplary engineering company. Of course, it's not constant. As you can see here, it fluctuates heavily, which is usually the case. The available hardware infrastructure is of course constant and does not change often for many years, since the process of acquiring new hardware is usually a very complicated process and many people are involved. If we now overlay the hardware demand on our available hardware capacity, we can see a clear mismatch of these two curves. We have here in green the part that is our used HPC capacity. In blue, this is where there is a low hardware demand, but we still have the hardware since this is local infrastructure, and therefore the hardware is not active. It's basically wasted capacity. In yellow, the engineers need to wait for freed up HPC capacity, or they use a lower core count in the simulation, which increases the simulation time. No matter how this flat HPC capacity curve, no matter where this is positioned, even if it's higher or if it's lower, there's always a mismatch, and it's impossible to avoid wasted hardware or these waiting periods. So the idea now is to reduce the amount of local infrastructure or even eliminate it. And to cover the high demands, use public infrastructure, public hardware resources from the cloud. If we again make this comparison with the reduced local capacity and cloud hardware with our hardware demand curve, we can see that there's some part of utilized local infrastructure, we have a much lower wasted capacity, and everything that is high demand can be covered by cloud hardware. So to summarize this short example, fit your hardware to your demand by the simulation and not the other way around. So just increase the utilized hardware whenever it is needed. When using cloud hardware, there's also no heavy investment involved. So everybody, especially also small companies and freelancers, can even afford this solution. And therefore, with no big investment, there's also no risk. If someone just wants to try it, we can try it, and if he's not satisfied or it's not needed anymore, you can just stop, which is basically impossible if you buy a cluster. And another plus is that the load factor is inherently equal to 1. So you always just have the exact correct amount of hardware for your simulations. Last but not least, it's a really easy setup, and also remote access is very easy. And for this reason, for this part, you don't need an IT professional. Everybody can do this. So a big advantage is the scalability. If you assume that you have some local cluster, then every simulation gets queued in the cluster and is worked through sequentially. In the cloud, you can also create a cluster, but instead of doing this sequentially, you can do it in parallel. So even make 3 clusters at the same time. The benefit is that the engineers are happy since there are no more waiting times, and the work is done in generally sooner. Since it's the same hardware compared to when it's done sequentially, there's no increased hardware cost. The same can be done for one single simulation. Instead of using one CPU, you can use 4 CPUs at the same time. So you got 4 times the hardware, but for a 4 times reduced amount of time. So also here, no increased hardware cost, but a sooner simulation result. Let's make a quick real-life example of the cost involved. The example used here is this backward-facing step. So this is just a sudden area expansion. And this was calculated in CFX with a mesh with almost 4 million nodes. So let's use a hardware. This is a H16 machine on Microsoft Azure. This got 16 cores. For the license cost, we assume to use ANSYS license as a service for solver and HPC. So in this graph here on the left-hand side, we can see the hardware cost and the licensing cost on an hourly basis. So since the simulation has run for a little bit more than an hour, the total cost involved with this simulation is $40. Let's see what happens if we now increase the core count. So let's take a bigger machine and then even cluster this machine, and let's go up to 480 cores. Of course, hardware and licensing costs is increasing dramatically, but we can reduce our simulation time from a little bit more than an hour to about 135 seconds. So the only thing that matters in the end is the total cost of the simulation. So by multiplying the hourly cost with the simulation time, we get the total cost. And this could be reduced from $40 to about $8. So by parallelizing a simulation to the extreme, you can really save money in the end. And of course, you are done much, much faster. So for the next benchmark, also this backward-facing step was utilized, and it was scaled from a width of 5 centimeters to a width of 20 meters in order to have the same characteristic variables like Reynolds number or CFL numbers over a wide range of mesh sizes. With that approach, mesh sizes from 72,000 nodes to over 20 millions could be used, and the simulation stayed basically the same. The performance was then evaluated by dividing the number of mesh nodes divided by the time used for the entire simulation. Here in CFX, we can see that for a HD44 cluster, we see some performance decrease for the lowest core count. This was here 1 million cores, 1 million nodes, mesh nodes on a cluster with 480 cores. For the biggest mesh, however, that was tried here with 20 million nodes, we can see that it stayed almost linear, even with a very high core count. For ANSYS Fluent, there were a few of the official benchmark cases, like the aircraft wing with 2 million cells, and this still had a very good scaling for up to 8 computation nodes, which was about 320 cores. This is not really a big mesh, but there's still very good scaling involved even here. The big and probably most famous benchmarking case, the race car with 140 million cells, was tried here on a cluster with 24 nodes, which gives about 1000 cores. So this was compared to the scaling, this was compared to the performance of 2 nodes, and we have the perfect scaling would be 12 times faster, and we reached here 10.9, which is a very good value when you think about that there were 1000 cores used for this simulation.
Creo is a 3D CAD solution that helps you build better products faster by accelerating product innovation, reusing the best of your design, and replacing assumptions with facts. Go from the earliest conceptual phases of product design to manufacturing to fully deployed smart connected products in the field with Creo. In the fast-changing, highly competitive world of industrial IoT, no other company can get you to sustainable value as quickly and efficiently as PTC. Emerging technologies are disrupting many aspects of the design and manufacturing, driving a renaissance of design across industrial manufacturers. PTC is taking these technologies and deeply integrating them into the Creo design environment so that you, as a design engineer working with your everyday CAD tool Creo, can use them as part of your existing workflows. Something that is unique to Creo and PTC. Let's have a closer look at the latest version of Creo 7. The latest version is 7.0.2.0, where we added many productivity enhancements and new multi-body capabilities. Besides this, our partnership with ANSYS has been taken to the next level regarding real-time simulation and Creo ANSYS. Furthermore, generative design capabilities and new features around additive and subtractive manufacturing were added here. Let's focus on the ANSYS powered products and get you a better understanding here. Product development companies and teams that we speak to every day are striving to achieve improvements in these areas. They want to get a better understanding of how their product performs in the field. They want to shorten the development cycle times and get their products quicker to market. They also want to reduce the design cycle times, so also there faster and quicker time to market is their goal. They want to reduce the number of prototypes and increase the first-time quality with a reasonable amount of money. Reducing warranty and liability is also a very important goal here. So let's look at the typical product development process. Often engineers feel they don't have the expertise they need to run simulations while they design. They feel like they need to consult an expert that may not even have access to every time. Often the expert's initial task is to figure out how to simplify a copy of the model so the simulation will run in a reasonable time, but still provide an actionable answer. Engineers don't feel comfortable making that judgment. Additionally, we can all agree that the design process is an iterative one. Certainly, the design engineer would want to use simulation as he or she evolves the design through all these iterations, but this would require running a simulation that could take hours on multiple unique simplified copies over and over. It's just not efficient. It's too disruptive to the design process, and so the design engineers generally just don't do it. This is the reason why we entered a partnership with ANSYS, with the overarching goal to remove these barriers for product development teams. We are bringing together two leaders in their respective fields and delivering a solution for our customers. We are going to remove the barriers we've just referred to. So what the product development teams really need is a simple tool that is so fast, so responsive, so simple to use that it can literally keep up with the design engineer every step of the way. No copies, no waiting, just simulation results right there throughout. A set of simulation capabilities that actually be pervasive across the concept, detail design stage to the process. Our new partnership with ANSYS gives us the opportunity to deeply integrate their breakthrough technology into Creo and make this need a reality. This, in combination with the new hardware capabilities that the Microsoft Azure Cloud can deliver to the engineers. This starts with a new product we are calling here Creo Simulation Live. This is the solution that will give every design engineer what they need to truly achieve simulation-driven design. The ability to instantaneously understand how a design change impacts product performance is truly groundbreaking and only available with the solution that we are bringing to the market in Creo. It uses unique technology to deliver simulation results interactively as you design. This solution will complement our existing simulation offerings that focus more on the analysis that require higher levels of fidelity or are used as final validation steps, especially in calculation departments. Let's call these solutions the more traditional analysis that teams might currently use. Represented here by our Creo Simulation extension, Creo ANSYS Simulation, and the entire ANSYS product suite. Let's take now a closer look at Creo Simulation Live, especially here in 7.0.2.0. Creo 7.0 introduces fluid flow analysis to Creo Simulation Live with the new Creo Simulation Live Plus extension. The software gives users instantaneous fluid flow simulation capabilities and is integrated directly within the Creo environment. Designed especially for engineers, it has a high level of ease of use. You no longer need to worry about having CFD expert knowledge to run simulations. As you make changes to your geometry analysis, results will update dynamically. Creo Simulation Live Plus is fast, intuitive, and powerful.
So thank you very much for this interesting time together. And maybe you understood more how easy it is to drive innovation in your company together with Microsoft Azure Cloud and all these other ISVs. So if you want to have more information about that, please don't hesitate to contact Paul's HPC specialist teams, or otherwise check out our website, desktop.studio. Thank you very much.